This recording is going to cover the physiology of the circulation, start looking at hemodynamics, and this one is going to address the control of blood flow. And prior to talking about the factors that control blood flow, I have to mention pressure, because pressure gradients determine the flow of blood. So we have to have pressure to be able to withstand resistance before that pressure has to be enough to go against resistance to get blood, say, to the capillaries, to get blood through the circulation. The pressure gradients that we'll talk about will result in what we call hydrostatic pressure. So hydrostatic pressure is the fluid pressure that, in this case, the blood, it's conducted in all directions. And so if I have, I'm looking at, say, a hose, or it could be your blood vessel, it's pushing up against the walls, and it's a result of that, force exerted by that fluid. Now remember, fluids cannot be compressed, so pressure gradients will result in hydrostatic pressure pushing this fluid from an area of high pressure to low pressure. So what we're going to be doing is we'll first be looking at some factors that affect blood flow, and in other recordings we'll be looking at blood pressure, and we'll be looking at capillary exchange. We'll be looking at different things. So let's start with this. Here is a basic equation for flow. So according to that equation, you see resistance is R. That is the pressure of the wall squeezing in on the blood vessel. It's hampering forward flow. And then you have the delta P, which is a pressure difference. Think of it as your hydrostatic pressure. That's the pressure inside pushing against the wall. And according to that equation, if an increase in pressure has a direct relationship to blood flow, it's directly proportional. An increase in resistance, though, is inversely proportional to blood flow. So if I increase pressure, I'll increase flow. If I decrease pressure, I would decrease flow. But with resistance, if I increase resistance, since it's on the denominator, that would decrease flow. If I decrease resistance, that would increase flow. Okay, so let's look at what makes up these resistance and look at these other factors. Now, flow is a flow rate. It's a volume per movement time. Your total blood flow in your body is actually your cardiac output. So sum of all the flows to all those different organs in your body, add them together, that is your cardiac output. What we're going to be looking at things will affect blood flow in an individual vessel. So we're going to be looking at this equation right here. So let's look at that delta P first, that pressure gradient. I've harped on that gradients rule in physiology. Same applies here. The pressure difference between, say, 0.1 and 0.2. So what's the difference in pressure? According to that equation, the greater the difference, the greater the flow. So let's look at this picture here. Now, over on the left, you see this blood vessel, the difference in pressure from 50 to 10 is 40 millimeters of mercury. The one below it, the difference between 90 and 10 is 80. Well, that second blood vessel has twice the amount of blood flow as vessel 1. It's a direct proportional relationship. Now, it's a pressure difference. It's a delta P. It's not absolute pressure. So if you notice over here, the pressure difference is the same. This one, you have a much higher absolute pressures, but the difference between this and this, there's no difference in pressure difference. It's still 80 millimeters of mercury, so they have the same amount of flow rate. So it's pressure differences. So one of the things that could affect flow is the pressure difference. Well, what about what you see here? that resistance. That resistance is kind of impeding forward flow. So what things could affect resistance? Well, if you notice here, just the effect of resistance on flow, if, say, for a given same delta P, higher resistance has lower flow. So you notice from here, low resistance here, there's a much lower flow rate if you have a high resistance vessel. So what are factors that affect resistance? Well, I said this is a simplified equation. Well, this is the actual unsimplified equation. So don't freak out. It's just, I don't want you to get completely upset. We're going to ignore the pi and the 8 because those are constants. So we're just going to ignore those. What are the factors that make up resistance? So resistance includes this here, that there, and that. So let's just look at R by itself first. So the first thing we're going to look at, so this here is a Greek letter, eta. And what that Greek letter stands for is viscosity. The second one, I'll erase it so you can see it. This is the Greek letter lambda, and these are actually the lowercase Greek letters. Can't spell viscosity. The L stands for length, or the lambda stands for length. So those are two Greek letters. The R is radius. So let's look at viscosity first. According to that equation, actually let's go back here real quick, according to just the equation for resistance, the viscosity, the Greek letter eta, the more viscous something is, the higher resistance. The less viscosity, the lower resistance. So what creates viscosity in your blood? Well, the primary thing that creates the viscosity in your blood is the formed elements. The majority of the formed elements are red blood cells. So if you notice, we got plasma, just a slightly more viscous than water, and that's the watery component of your blood. But when you have all those formed elements in there, you'll notice the viscosity is greater here. And it's because of all the red blood cells that we have in there. So the more viscous it is, think of it as the inherent stickiness. Things are not going to want to kind of move against each other. The more resistance. The more resistance, the less the blood flow. Okay, so going back and look at this equation again. Higher resistance here means lower blood flow. So while I'm here, I might as well mention, so here is the equation for resistance, and all they did was rearrange this. And so what they did is, this is the rearranged equation, and they simplified it, and they got that. Okay, so you'll notice on this here, if I increase viscosity, it's on the denominator, I will decrease flow. So viscosity can affect it. Now, normally, normal blood, we have a consistent viscosity. Can't really day-to-day, second-to-second change viscosity to affect your blood flow. But if your number of red blood cells is altered, that could affect viscosity. If someone is anemic, they have less blood cells, there's less viscosity there. If someone has something called polycythemia, they're overproducing the red blood cells. They're not mature, but they're overproducing them, but that's going to make blood more viscous, which would affect resistance and affect blood flow. Now, the next thing to look at is, is the length. Okay, so that the lambda is length. Greater the length, the more resistance. More resistance, the less the flow. So think of it, actually, a lot of the resistance that comes apart from blood going through blood vessels is friction between the vessel and the blood. And a lot of that friction comes from going along that blood vessel. So the longer the vessel, the greater friction we're going to encounter. The shorter the vessel, the less the friction. I want you to think about, is that something that if I want to just alter blood flow within a couple seconds, am I going to be able to alter the length of that vessel? Do you think that's reasonable? Oh, let's shorten up this blood vessel. Let's cut pieces off. I don't think that's going to happen. So changing the length of a vessel is not going to be a major way of physiologically controlling blood flow. Changing the length of the blood vessel would maybe happen, or we say that this is only going to be something like if someone put on a lot of weight, going to have more blood vessels there to serve that adipose tissue, they will encounter higher resistance. But physiologically, no, this is not something we're going to change. What's even more important is looking at this R, the radius. The friction can depend upon the wall, the radius of that blood vessel wall. So here, if you look at this picture, you see you have a radius of A is 1, the radius of B is twice the amount. Notice you got much more water into this container than here, and it was not direct. It was actually, or we say it's direct, but it's not proportional. It's to the 4th power. So we, as a result of doubling the radius, I increased it by 4-fold. Actually, not 4-fold. I think it's 16-fold if I did the math. So yeah, 16-fold. So because of it's R to the 4th power, so it's 2 times 2 times 2 times 2. That is 16. This has much more dramatic effects on flow. If you increase the resistance, if I increase the radius, we'll do it this way. If you increase the vessel radius, that actually decreases resistance, and it increases the flow by a lot. If you decrease the radius, that would increase resistance and decrease flow. So because of that R to the 4th power, that has much more dramatic effects. And I'm just going to show you mathematically here. So if I double the length, I have increased resistance. Notice I've gone from 100 cubic centimeters per second, which actually cubic centimeters a mil. I halved it. Okay, so you double the length, you halve the flow rate. If you double the viscosity, that also increases resistance, and it halved that flow. Okay, so it's pretty much direct. If I double the pressure, because Q is equal to delta P over R, that's going to have a direct effect, and that's going to increase flow. And so I'm doubling it. I'm going from 100 to 200. Okay, so those are straightforward. Radius, if I double the radius, that doubling the radius is going to decrease resistance. Not going to encounter a lot of friction on the wall because you made that vessel diameter get bigger. Notice what happened to flow rate. I've doubled it. I have a 16-fold increase in flow rate because it's R to the 4th power. And remember, just so you know, radius is half the diameter. Okay, so that's radius. This would be the diameter. So think about the significance here. A changing vessel radius is more ideal for altering blood flow than anything else. It just doesn't seem easy just to alter viscosity, because I'm like, it takes time to change down to red blood cells, and that's going to affect a lot of things. So I'm like, no, I'm not going to change viscosity. I'm not going to change the length if I want to just short-term alter blood flow. Now, what about pressure? Well, pressure, you don't want to change pressure because that would have more global effects. And the heart would have to work quite a bit to be able to increase pressure, and have to increase pressure everywhere in your body. Changing the radius makes more sense. And so we're going to get there. We're going to show you. Okay, we're going to show you something. So let's just look at some clinical applications first. or some checking the concept. So here's a blood flow, vessels A through D. Okay, so they're branching off of this vessel here. Flow rate is 4 liters per minute. Notice all these add up together, 4 liters per minute, because the total flow rate's the same. What happens if I narrow this vessel? What's going to happen to resistance in vessel B? Okay, so I have decreased the radius. What happens to resistance? That's the first thing you need to answer. What happens, therefore, would happen to flow in vessel B? So remember our equation. Flow is delta P over R. Now, also, the last question is total flow affected? So I want you to think about it. Let's go. So notice, flow rate in B decreased because you increased resistance. What happened is we've diverted some of that blood to the other vessels. So these increase. When you do the math, they still end up with 4 liters per minute. So total flow didn't change. Is what we've done is we've restricted flow to one vessel to allow more flow to go to the other. And this is how our bodies work. When you exercise, I'm going to increase blood flow to those working muscles. I'm going to divert blood away from parts of my body that I really don't care about at that particular time. So I'm going to divert blood away from the GI tract, get blood to those skeletal muscles, for example. Here's some other kind of concept, looking at those concepts in just a different way. You sip a milkshake versus a soda. Okay, which is more viscous? The milkshake. That's harder to suck up. If you want to try to be able to drink is the same amount of volume per unit time, you're going to have to create a higher pressure to be able to get that milkshake up. So this is more viscous. Same way if I'm going to fill up a jar with water versus honey. This has a higher viscosity. And so I'm going to be able to fill up a jar a lot slower with honey than I am with water. Okay, so that's showing you viscosity. Here's a hose. We're trying to empty out this container. The shorter hose versus the larger hose. This is going to empty out, take longer than here because it's going to encounter friction as it goes down that longer hose. And so if I want to, we can do it the other way. If I want to fill something up, I want a shorter hose as possible than a long hose because it's going to take a lot longer to go through that hose is going to encounter more resistance. So this looks at the length. Okay, last one. Let's look at drinking something. So the cocktail straws, or even like the straws they use at the gas stations for the coffee, they're really small. Can you imagine drinking a milkshake through that? You'd probably pass out. Notice in some of these, they have wider diameter straws because these are very thick. It'd be hard to kind of suck that stuff up, so we have to have a larger radius. So the larger radius is going to have less resistance and so be able to increase flow. So this is looking at radius. All right, so those are going to be, so again, I'm going to write this down, very important equation. Flow, you can use this equation. You don't have to memorize that full, big, long equation, just so you know what resistance is. The factors that make up resistance includes length, viscosity, and radius. And it's radius to the 4th power. Increase this or this, that increases resistance. If you decrease those, that decreases resistance. If I increase radius, that decreases resistance. If I decrease radius, that increases resistance. And therefore, if I increase resistance, I decrease flow. If I decrease resistance, I increase flow. Just try it out. Just put some numbers here. So if I have, say, 4 over 2, that's 2. 4 over 1, that's 4. So I decreased resistance, flow went up. 4 over 4 is 1. I increase resistance, that's less flow. Just plug in some numbers and you can see it. Okay? So we're going to stop here. Next one, we're going to look at another concept associated with the circulation.